Thank you so much. Thank you so much, Antonella, for the generous introduction, and to the organizers, Gabor and Antonella, and all of the organizing committee for inviting me. And thanks to the University of Luxembourg for hosting us and hosting me here. And thank you to all of you for coming to hear my talk, especially on a beautiful day when you could be outside. So I'm going to talk about accelerating scientific discovery with open source AI models. Actually, I should have said AI models and data, and I'll tell you what I mean by that in a minute. So it's nice to be back at Journées Arithmétiques and in a number theory setting. And I know this is a public lecture, so it's trying to be a little bit more focused towards the public. But at the same time, I understand that many of you are here for the number theory conference, so I will try to get back into the kind of mathematical and number theory side of things in the second half of my talk. So let's see. Because I assume that many of you are number theorists and not AI researchers, I wanted to start by saying what we mean by AI. So today in the high-tech industry, we're using the term AI, artificial intelligence, really to refer to what computer scientists have referred to for quite a while as machine learning. So artificial intelligence is really just the science of using data to train mathematical models that predict outcomes with high assurance. So when you think about that, like, there are a couple things that we should emphasize and we should remember. AI outputs are really just like high probability predictions. That's what they are. And they are output by mathematical models that we decide to train. So we decide what data to use to train them, what type of model and what type of training procedure. And then in the end, we have a model which can be used to make predictions. So I like to describe the machine learning pipeline. I actually just put it on the slide up here, just to be clear about what I'm talking about. The first stage of doing machine learning or an AI is collecting data. So in fact, for more than a decade, whenever I've talked to any kind of applied machine learning group, anybody working on training models for some kind of practical purpose, they will tell you that a huge amount of the time and effort goes into just curating the data. So cleaning the data, curating it, whatever. And in fact, I think that's one of the areas where we're still underinvested in the rush to large models and large language models, is on that first step, which is on curating and understanding data. And in fact, there are some rather horrifying stories about people, academics, for example, training models on large data sets without really knowing what kind of data is in that data set, and ending up finding out later really bad or objectionable data that can be contained in data sets that you're training on. So that's one big whole area, is just data collection and curation and understanding. And if we make more progress there, it may help us in making our overall machine learning pipeline more efficient. So the second part I refer to is really the training process. So you've decided on some kind of a mathematical model that you're going to train. You could think of that as being like the shape of the model, or the process that you're going to use, the mathematical operations that you're going to perform to train this model. And you're training the model really to do some task. And then the next stage is, once the model is trained, it can be used in practice for inference. So then you come along with some new data and you give it to the model, and the model will output a prediction. So I usually have a slide in here that has a ton of applications. You can think of anything from financial area of, if you think about credit card companies that want to protect you from fraud, and you buy something with your credit card, you make some kind of transaction, and they have a model and they want to predict, is this likely to be a fraudulent transaction? Or is this most likely kind of what we expect from this particular customer? You can look in the health area, an area that I'm particularly inspired by, where you can have AI being applied to, for example, radiology, understand it and helping improve medical imaging, both improving accuracy or bringing down the overhead and the time for medical practitioners to be able to analyze medical images. I worked for a long time in genomic privacy, so AI can be used to analyze genomic data. So there's many different areas in society where these types of algorithms can be trained and then used for beneficial purposes. So I'm just going to say a little bit about the mathematics behind machine learning. I think we too little talk about what's actually going on underneath. And if I didn't have so many other slides, I would spend more time on this. But I like to explain that the basic idea behind supervised learning. So supervised learning really means that the data is labeled. So if you imagine, if you just have a binary classification problem, so you just have two labels, like a 0 and a 1. So all your data would be either labeled as a 0 or labeled as a 1. So one of the nice concrete examples that I like to use from more than 10 years ago was a colleague who was analyzing medical images. These were actually pictures of liver tumors. And the idea was, this is a binary classification problem. We have a patient who's come in and they have some kind of tumor, and we're going to do some medical imaging. And now we'd like to predict, is this tumor likely benign or malignant? And you have a lot of other patients who have already been treated at your clinic, and their data is available to you, and it's already labeled. These were people where the tumor was benign. These are people where the tumor was malignant. And so absolutely the simplest mathematical model that you can think of that I think kind of exemplifies the idea of machine learning is what is called a linear means classifier. So you basically take your two clumps of data, these data points, and this could be in very high dimension. For example, these images of the tumor, each patient had about 20 to 25 different measurements of their tumor. And so those are like, let's say 20 features. And each of these patients is labeled either 0 or 1. And so in high dimensions, you can think of, imagine the cluster of data points in high dimension, which represents the patients that had a malignant tumor, and another cluster, which is those whose tumor was benign. And so you actually just compute the mean, and then you compute essentially the vector in high dimensional space that connects the two means, and you compute the hyperplane that separates them. So that's a very simple mathematical idea that then what you've done is you've actually computed what I like to call a decision boundary. So this hyperplane is very, very simple, but it's a decision boundary. So now a new patient comes in, you do all those same measurements, you basically decide, well, was the patient on this side of the hyperplane or that side of the hyperplane? Okay, so the only reason for explaining this very, very simple model is to just try to give you the idea of what's happening in AI and machine learning underneath, is that some recipe is being used to train some mathematical model, and then that model is being used to make predictions that are hopefully useful. So as you can imagine from that simple model, it could very easily be wrong. Like you could have patients that were near that decision boundary, or a new one comes in, it's just on the other side, and you make a wrong prediction. Yeah, that's what happens in AI. So I think that's one of the fundamental things that I would love for you to take away from this talk, is that there's a lot of gloom and doom about AI and its potential and everything. But remember, it's just mathematics making high probability predictions. That's what it is. So until we get something different, some other technology, you don't have to be too worried about it. What we need to worry about is how incredibly inefficient it is, how to make it more accurate, how to make it more useful, all of these things, and how to avoid humans misusing it, which is the big worry in my opinion. So on the mathematical side, I've just listed a few of the other options that are more sophisticated. So in practice, the models that are still actually very powerful just using linear regression or logistic regression. And so those can still be very useful machine learning models. But the large language models, or the large models that you hear about in the media these days, are typically these deep neural nets which you can think of as like just many, many layers of logistic regression piled on top of each other, and transformers, which are some particular optimizations for those. So in practice, those are the models that are being chosen to be trained. And then the mathematics of how do these things get trained in practice, and a little bit more complicated than the linear means classifier that I described. The idea is to define a loss function. So in your data points, you've got, and we don't just stick to binary classification problems. The problems are much more complex, like next token prediction in language. The possible tokens are many, many possible tokens. And you're learning like a distribution, a probability distribution, and the model will output like the most probable next token. So the way that this happens is, so defining a loss function is the loss is simply the difference between whenever you have a model, let's just freeze a choice of your model during your training process. And you take one of your data points you're supposed to be analyzing. Well, look at the data point like input, output, and then look at your model, put that input into the model, and then see what the output is and see how far it is away from the actual output that it was supposed to be guessing. And so this, whatever you define as your loss function, is your way of measuring that distance. How far away are you from what it was supposed to predict? And so what you can do is you can think of a very, very high dimensional space, which is the space of possible models. And when you're training, you basically start at a random point in that space. Just can be actual random initializations of the weights of your model. And then you want to walk from that random starting point to a better point in the space. You want to walk to a better model. And you do that by always trying to find a step in the space of models, which is improving how good your loss function is doing. So you want your loss to drop. Your loss is how far you are away from the right answer. And you want to get closer to the right answer. So you're trying to minimize your loss. So as you can see, what are you actually doing? It's basically multivariable calculus. You're on some huge dimensional space, and you're basically taking steps around this space, trying to find a minimum, or a local minimum at least. And so I like to say, like many million dimensional space, and you're walking around trying to find a minimum. What could go wrong, right? So obviously there's a lot that could go wrong, and there's a lot of theory that goes into trying to improve this process. But I wanted to start by just kind of explaining the process of machine learning as the foundation for my talk. So the thing that's really interesting today is that over the last few years, there's been a lot of debate and controversy over the idea of open models, open data, open code, all of these things. So that was actually one of the things that I really enjoyed the most in my career, is going to Facebook, at the time now called Meta, where the philosophy is really to release everything openly. So they actually acquired a startup called Papers with Code at some point, and the idea is that FAIR is a basic research lab who publishes all of their research, but not only publishes, every paper is expected to be released with the code and hopefully the model. So up until now, we're still releasing all of our models. Let's hope that it stays that way. And so whenever people say the word open, always just be a little critical and just think, well, what do you mean open? So first, just publishing the details of your work and your model, that's important. But second, are you providing the code? Third, are you providing the trained model? And fourth, are you providing the data that it was trained on? So you really need all four of these in order for the work to be replicable, right? And replicability is very, very important in science, right? So the way the machine learning community has handled these challenges for a while, like over the last decade or so, then this means academic researchers and industry researchers, is that in any given field, for example, computer vision, some standard data sets are developed, and then everybody can do their work on those standard data sets. And then that's great. You don't have to release your data. The data is already public. Everybody knows about that data, and they can all use it to compare, your paper, your code, and your model. Just one other point about this is that the difference between number 2 and number 3 might not be obvious, right? So if I just write a few lines of code and then I run it on a small amount of data and I compute a simple model, then it doesn't really matter if I give you the code and the model. You can take the code, you can run it, you can get the model, right? But where there's an asymmetry there is in today's day and age, where what's happening primarily in high tech at the large companies is that the amount of money and compute time and data that's spent to train the large models is equivalent to hundreds of millions of dollars and a lot of energy as well. And so in that case, there's a huge difference between number 2 and number 3. Like, yes, you can share your code, but if it's going to cost another, let's say a startup company or some academic research group, if it's going to cost them hundreds of millions of dollars, months, and tons of energy of compute in order to replicate your model, it's a lot more efficient in every one of those senses to just actually provide the model. So when I say open models, that's what I'm referring to. I'm referring to actually sharing the models that have been trained and sharing them openly so that people have the actual weights and they can use the model as a starting point for their research to go further and continue training in certain directions, which is called fine-tuning and that kind of thing. So I'd like to give some examples of some of the work that I'm very proud of. I think many of you who know me as a number theorist may be wondering what I've been doing for the last 4 years. And I've never been busier, and I've never learned more in my entire life than I've learned in the last 4 years. And it's so exciting. It's a time when the field has just been accelerating, and so much great work, but also, honestly, a lot of craziness. So competition and the accelerating pace of research has been quite overwhelming. But just to give you a couple of examples, just in the year 2023, these are open models, open source models that were released from FAIR. All of these projects were either fully or partly done in my org in FAIR. They were either started or completely trained in my organization. So Llama, for example, which started with FAIR, the first Llama models were in 2023, Llama 1 and Llama 2, and in 2024 and 2025, we have Llama 3 and Llama 4. And to this date, we know that there have been more than 1 billion downloads of the Llama models. So I'll talk a little bit more about what type of work that enables, the fact that the Llama models are openly available. So lots of other examples. I'll just highlight a few. So the segment anything model is a model which helps you segment images. It can also, SAM2, segment anything model is called SAM, and SAM2 is for video. And so it can help, for example, I'll give you some medical images where SAM is being used to help analyze medical images. Same thing for Dino, analyzing medical images. A few other really fun examples. So massively multilingual speech model is a speech model that works on low resource languages. So we're actually currently starting a project with a clinic in Nigeria, trying to help patients coming into a clinic that don't speak English. So the MMS model is actually trained on some Hausa data and is able to help transcribe and translate the conversations between doctor and patients into English. And so this is the kind of thing that is not possible with most of the mainstream language models that are focused on what you might call high resource languages. So that's another project that's ongoing and very exciting. And for example, Seamless, which is our speech-to-speech translation model, we just released a new version of Seamless this past week. Seamless was voted Time Magazine Invention of the Year in 2023. So lots of exciting examples of releasing models openly. So these are all models that were released. And then here's just a few examples of the ways that these models have been used. And I actually hosted a whole open science conference in May in Texas on medical and scientific applications of these models. So we had a lot of medical practitioners and people from startups and a lot of other fields of science coming and talking about how they use the open models in their scientific inquiry. So one thing that's very exciting is there's been a whole family of Llama models tuned for medicine. So MedAlpaca, LavaMed, Metatron, LlamaMe. These are all efforts. These are external efforts, not done by Meta or FAIR, where medical researchers have taken medical data and continued tuning, like fine tuning, we call it, or continued training the Llama models so that they're better at recognizing the medical terms or the medical images that they're meant to do. So that makes it into a higher quality model for medical purposes. And actually, just to go back to the example I gave you of the Hausa speech recognition in Nigeria, the idea there is that by using our MMS model in that context and collecting more data of native Hausa speakers, that then potentially we or other parties can continue to train those models to make them even better on recognizing the language. Okay, so MedSam, Medical SAM, it does medical image segmentation, and it again was developed by an external group to continue training the SAM model to make it better at being more useful for analyzing medical images. Another model I mentioned coming out of FAIR, the Dino model, has been used, for example, for computational pathology by a lab at Harvard, by Oracle for analyzing oncology, by Virgo, another startup doing endoscopy. So lots of different examples in the field of medicine that I'm very excited about. So I'm going to talk about two more examples in science before flipping back over to some mathematical applications. So the next example I'd like to talk about is chemistry. We have a FAIR chemistry project led by Larry Zitnik in my org. And what the chemistry team is doing is realizing that there are many real-world problems that we may want to solve, which require working at the atomic level. So for example, drug discovery, discovering solutions for climate change, such as direct air capture, or materials design, which can be important for tools of the future, for example, augmented reality glasses. So there's a whole set of problems, both scientific and commercial or business related. and they require working at the atomic level. And so I've just had a crash course in chemistry over the last 6 months that I never thought I would have. Because the interesting thing is that the way that AI is being used in this field is that it's really going to be a replacement for, or it's already a fairly high quality replacement for what we call DFT calculations, density function theory. So there's several areas of science that I know of. For example, weather prediction is the example where I've worked before, where you take data that is reflecting the physical reality, and then there's a bunch of physics models, basically partial differential equations, that model what is supposed to happen. And for example, in the US, the national laboratories are the only ones that have the real compute infrastructure to be able to do the kind of numerical analysis on this very vast, data that's collected for weather prediction in order to do high quality weather prediction. And so one of the interesting breakthroughs in the last 5 years or so that I was really interested in is the ability to replace some of those physics calculations with AI and to make that computation lighter so that you can do high quality weather prediction, quickly and more easily and with less specialized compute infrastructure. Now, the same thing is happening in chemistry with this project. So this project has started, Larry Sitnick started this project about 5 years ago. And all of these are just acronyms for different data sets that they released over time. And the most recent data set that we released in May, the Open Molecules data set 2025, is a data set where what they did was they collected, there were like actually 12 or 13 data sets from different branches of science, so reflecting both material science and evolutionary biology and organic chemistry, and worked with partners who were subject matter experts in those fields who were doing the traditional path, which was running these DFTs, which are the analog of what I told you about the weather prediction. They're solving these basically partial differential equations that come from physics. And so by doing a huge amount of compute of these DFTs and then training AI models on that data to actually do the DFT predictions, what they've been able to do is to release the largest ever data set, it's called Open Molecules data set, which takes some initial configuration of atoms and then predicts what is like the energy state going to be after some interaction. And it will show both the energy and the new configuration of the atoms. So one of the things I was most impressed by is that the team estimates that we spent 6 billion CPU hours to compute this data set. So this was all done using harvested compute time from our commercial infrastructure, so cycles that were not being used for running the business. But if you translated that into dollars, I don't know what the number is, but we're talking hundreds of millions of dollars. So far, the field externally, the reaction has been very positive that it's the type of data set that can be useful in so many different fields of science and can potentially change the direction of many fields of science. So this is why I said in the beginning, my title, I should have said the impact of both open models and open data. In this case, it's the data set, which is so valuable and important, and it's openly available. But the team also trained a model called UMA, Universal Model for Atoms, and has released the model as well. So the last example from science I wanted to talk about is a team that I'm very proud to manage and support is our neuroscience team. So we call them Brain and AI, and lucky for me, they're based in Paris, so it gives me a lot of extra reason to go to Paris. And so they are working on trying to understand the human brain. Like their goal is to develop a model of the brain. That's what they're working, the human brain. So there are there are plenty of other labs around the world working in neuroscience and many leading labs doing amazing work. But my understanding is that, for example, like the Allen Institute is primarily focused on like the mouse brain, whereas the work in our team is really primarily focused on understanding the human brain. So working on understanding both the visual cortex and speech right now. So as an example, so I won't go into too much detail, but the reason I like this picture, so I've got, you see there's a bunch of blue dots up here and a bunch of blue dots here. So the idea is the method, the work is following is that this represents deep neural nets, so mathematical models that can be trained. And this represents the brain. This is basically brain sensor data. So brain sensor data historically could be collected only through invasive technology. So when we have access to epilepsy patients who actually have implants in the skull, you can get more fine-grained information. But what's been exciting over the last 5 to 10 years is access to non-invasive brain data. So these days, we have a drawing of that nice machine, but I don't have it on my slide. But it's imagine a machine that is about this tall and very, very large, and patients sit inside of it. And only a limited number of hospitals have this, and so you can imagine the amount of data we can collect is very limited. And now what we're starting to see is helmets that can actually just sit on top of your head and collect the brain data. In fact, one of the fun things that I got to do a few years back was to be interviewed for Werner Herzog's documentary on neuroscience and the brain. And it features these helmets, and it shows how we're able to collect brain data these days. So if anybody's interested, you can see Werner Herzog's new movie documentary that's in theaters. It's called Theater of Thought. So it just represents that our ability, like many other areas of AI, our ability to do science in this area is accelerating because we're able to collect more and more data, and we're able to develop these AI models quickly to understand the brain. So the example that I like to show is a model that we released in May. Sorry, which way am I going? Wrong way. So this is an example where what we do is actually, and the team is led by Jean-Remy King in our Paris lab, is they show a patient this image here on the left, and then so the brain signal is observed. How does the brain react to this image? And using models that they've trained, they're able to match it up and predict what they think that the human saw based on the brain signal they recorded. And these are the predictions. So you can see the faces are just purposely blanked out there. So you can see that in this setting for images, we're getting some kind of reasonable signal of what the brain is recognizing. And the next stage for this project is to actually be able to handle video. There's other examples that were represented up here. In January, we released the ability to decode human typing, for example, so language focused. So this work is very, very exciting, and I could probably talk for the whole rest of the time on the neuroscience, but now I'd like to move on to my final application, which is my own research using AI in cryptography. So also in May, we released new data sets, which are hopefully helping to accelerate the field of AI for crypto, which is a field that we started about 4 years ago. at FAIR, and which involves training machine learning models to attack and probe the security of public key cryptography or post-quantum cryptography. So you could argue AI for crypto, should it also involve, there's other researchers, especially in Europe, who are working on using AI for example, for side channel analysis. So those are also could be called AI for crypto, but when I say AI for crypto, I'm specifically talking about our work, which is attacking public key cryptography. So what we did in May was to release very large data sets that can be used by others who are machine learning researchers who don't want to have to produce and curate the data sets. They want to just directly work on improving the machine learning models. Okay, so again, going back to my title, open source models and data for accelerating scientific discovery. So I gave you kind of three examples of big releases that we did in May, and that was the chemistry and the brain and now the crypto. And chemistry was data and a model, brain was a model, and crypto was data. So it was like examples of each of those. And in the case of Llama and the innovations in medicine, it was that's an example of the Llama model being released openly. Okay, so let me go into a little bit more detail on the cryptography side of things here. So for the number theory audience. So the idea here is that starting in 2017, NIST ran what's called post-quantum cryptography competition to select new candidates for public key cryptography to assure the security of the internet going forward. And in 2022, some systems were standardized. So cryptography is used in almost everywhere, the science of keeping secrets and protecting privacy and authenticating your transactions. But in particular, you yourself, when you go online for any kind of secure browser session, also if you use encrypted messaging on WhatsApp or Messenger, these are all using public key cryptography. And the post-quantum cryptography really refers to the fact that the systems that are deployed today based on hard math problems such as factoring, the RSA system, which was introduced in the mid-70s, or for example, elliptic curve cryptography, which is based on the hardness of the discrete logarithm problem in elliptic curves, which was introduced in the mid-80s. So these problems, once we have a full-scale quantum computer, we'll have polynomial time algorithms based on Shor's algorithm, which will break these systems completely. So once we can get a big enough quantum computer built, we will no longer be able to use these systems. So that's what the term post-quantum cryptography refers to, is we want new crypto systems that will not be broken by a quantum computer at scale once a quantum computer is built. And we already have some, small-scale quantum computers, but it's not at all clear how fast the development of a quantum computer will develop or accelerate, or if there will be any, discontinuities, disruptive breakthroughs. So for the last 3 years, since 2022, we have some standardized PQC systems, and there are now conferences in the industry of people working full scale on trying to get these new systems deployed. So for example, lattice-based systems and code-based systems and multivariate-based systems. Supersingular isogeny graph systems are not being deployed. Despite the fact that the hash function that we introduced based on them in 2005 is still not broken as far as I know. But the key exchange is broken, so they're not implementing that one. So I'm going to focus the rest of the talk on lattice-based cryptography. So we have a very simple version of lattice-based cryptography that I like to use to explain to the public. So the system is called learning with errors. And even like this is literally the only equation. Sorry, let me go forward one. This is the only equation on my slides. And it is really representing the fact that learning with errors is really given many pairs A comma B for a fixed secret S. The learning with error problems is simply to be able to find S given A and B, where B is just a noisy inner product of A with S. So just imagine from your point of view, let's say you're the person with the secret and you want to encrypt something. So you have a secret vector S. So the number of entries in your vector is what we call the dimension. So you've got a secret vector S with n entries in it. And every time you want to encrypt something, what's going to happen is you're going to generate n random entries in a vector, which we're going to call A. You're going to take the inner product of A, which is just component-wise multiplication of the entries of A with the entries of S, and then add them up. So the inner product of A with S. And then you're going to add some small error. The error is usually assumed to be a very narrow Gaussian, so just some noise, basically. And the noise gets added to each of these inner products. And so you're given, that's why it's called learning with errors, because you're given a bunch of random vectors A and a bunch of B's that go with them. And the first problem is even to be able to detect whether these are learning with errors samples. Was B constructed as an inner product with the secret, A with the secret plus some error, or is B just random? So that's the decision problem. And then the search problem is to actually recover S, the secret. So that's the learning with errors problem. And so a little spoiler alert. The reason that I actually really wanted to go into this area and work on this problem is that, so I worked on learning with errors for about 10 years on applications for protecting privacy using homomorphic encryption. Because all homomorphic encryption systems today that are available or deployed or being used, they're all based on the learning with errors problem more generally, but even more specifically, the ring learning with errors problem, where the ring is actually a 2-power cyclotomic ring, so it comes from number theory. But the learning with errors problem is that, that it should be hard given a bunch of data. So if you see, this is could be a huge amount of data. And now the hard problem in cryptography is, can you learn from this data? So given A and B, can you learn S? And so we were doing a lot of machine learning applications at the time. And so I was kind of working closely with machine learning researchers. And I thought, well, that's pretty funny. Cryptography thinks that this problem is hard. Learning with errors is hard. But machine learning thinks that this problem is easy. That yes, given a bunch of data, we can learn from this data. And so actually, it's only a small exaggeration to say that I went to Facebook to work on this problem. So I found a research engineer, Francois Charton, to work with me on this, and we hired 2 interns, and we started this project in 2021, and we've been working on it ever since. So this is what we found. So first of all, let me just give you a little context about the practical importance of LWE. So I told you that it's been used for the standard, standard homomorphic encryption, and it was also standardized by NIST. So these 2 slides are showing you the parameters for these 2 applications. So the thing to specify a learning with errors system and to know how hard it is, you need to specify all of these parameters. So I need to tell you what is the dimension, that's how many entries there are in the vector. What is the modulus? All the computations are done mod Q. What is the width of the error distribution? So how do you sample the error for all of these LWE samples? What does the secret vector look like? For example, is it a binary secret vector where all the entries are 0 or 1? Or is it random, like where all the entries are random mod Q? If it's binary, How sparse is it? Like, what is the Hamming weight? How many ones are there versus zeros? And finally, M, which is the number of samples which are given to the attacker who wants to attack this system. So I like to start with this slide and draw your attention to this red part right here. There are plenty of examples where LWE is not hard. So we think of it as being a hard problem, but that's only when we pick the parameters carefully. So for example, if you make Q, the modulus, too large compared to N, the dimension, what happens is that you can use the LLL algorithm, which is a polynomial time algorithm in the dimension, which runs in roughly time O of n to the fourth, to find short vectors. Well, it won't be the shortest vector, but if it's short enough, it can still break the system. And if you make Q large enough, it's easy for LLL to find a short enough vector. So I like this little cautionary tale. LWE in general is not hard. But what we do is we pick the parameters carefully, which is what's been done through decades of research on lattice reduction to try to understand how good and how hard lattice reduction is. And so, for example, the NIST 2022 standard, Kyber, is there's a 512 version and a 768 dimensional version, which are modules over a ring. Like I said, a 2-power cyclotomic ring in dimension 256, modules of rank 2 and 3. And the log Q is specified. Q is equal to like 3,329. The binomial secret distribution is specified. Every entry of the secret is either -2, -1, 0, 1, or -2, and following in a binomial distribution. So 0 is the most likely entry of the secret. And so you can see it's a small secret, but it's not necessarily sparse. It's only about 37% zeros in the secret. Whereas homomorphic encryption is a little different. The dimensions tend to be much higher. So for example, to enable bootstrapping, you typically have to have the dimension be 2 to the 15. And so log Q can also be bigger, which allows more room for encoding and encrypting valuable information. But log Q, for example, for 1024, log Q should be something like around 26 bits or 29 bits, depending on which version of the standard you look at. And so you can see the moduli are much smaller than in currently deployed public key crypto, right? If you look at RSA today, you have a minimum of 2048 bits. So primes are 2048 bits, whereas here, the primes are much smaller, but the dimension is much bigger. And homomorphic encryption in general does use small secrets. So binary ternary secrets, not even usually Gaussian, but also in particular favors sparse binary or ternary secrets for efficiency reasons, and also small error. So another thing that's important to realize is that decades ago, like the Darmstadt lattice challenges that were developed, they're not really relevant to what's been standardized and what's being used in practice. Those are general, lattice challenges in very small dimension with random secrets and general error, and not focusing on really small secrets, small error in super high dimension, which is what's done in practice. So I won't go into too much detail, but the classical approach that I've referred to of understanding lattice-based cryptography and its security relies on decades and decades of lattice reduction. The prototypical algorithm was the LLL algorithm from the 1980s, but it's been improved over time. And there's excellent open source implementations of generalizations of LLL, for example, BKZ, and newer technologies such as Flatter, which is a more efficient version of LLL, and BKZ 2.0, et cetera, et cetera. But the quality and the running time of these algorithms is still very ill understood, because in general, they can only be run in very, very small dimensions. And so that is one thing where we still need a lot of work. So instead of continuing to just keep working on lattice reduction forever and ever, I decided let's try something different. What if we use machine learning and try to see what machine learning can do in LWE? So that was the starting point of our project 4 years ago. And so first we had to come up with a plan. So what's going to be the data? What's going to be the model? What's going to be the task that we train the model on? So we tried different things, but we landed on just given samples A, comma B, which are LWE samples. The task is given A, predict B. So that's what we train our models on. We tried lots of different types of models, LSTMs, recurrent CNNs, et cetera. But we landed on using transformer models. And in fact, ML models are pretty good at learning from noisy data. So I'd like to point out that if we were not actually doing all of this work mod Q, then I wouldn't even be standing here. This problem would be over. Machine learning would just recover the secrets immediately. So the real problem is that machine learning algorithms today are absolutely terrible at doing modular arithmetic. So we were talking about challenges that Epic AI is putting out for AI to solve. How good is AI at doing math? Well, let's try just making AI be able to do modular arithmetic right there. So I'll mention a little bit later. We have a paper appearing at ICML next month, or this month, this July, which is showing being able to do modular addition at scale. And that is a pretty exciting use of different data strategies for making the models learn. But I ran a project at the Win6 conference, and we published the results like a year ago or so, training models to do modular multiplication. And modular multiplication is still not working well. It's still not scaling up to large moduli above like roughly 25 bits. So modular addition and multiplication are a challenge, and we are pretty convinced that progress that we make on modular multiplication and addition will translate into making more progress on these models. So in my last 5 minutes, I just want to kind of say what is the progress that we made? What did we find? So the models that we trained and released are called the SALSA models. It's secret recovery attacks on learning with errors using sequence-to-sequence attention. That's what SALSA stands for, but as you can see, it's kind of hard to remember, so just SALSA. And the papers are called SALSA, SALSA Verde, SALSA Picante, and SALSA Fresca, so that should be hopefully easy to remember. And those are published in top machine learning and security conferences over the last 4 years, along with 2 other papers, a Cool and Cruel paper from last year and the benchmarking paper, which just appeared last month at the Oakland IEEE Security and Privacy Conference. So the first paper, SALSA, was just a proof of concept. It really showed that we could train these transformer models, and we could get them to predict B from A, and then we could develop cryptographic distinguishers, which would use those models as an oracle to recover the secret. But we were only able to do very small dimension, like dimension up to 128, and very sparse binary secrets. And so the ingredients that we had in our SALSA paper, in our SALSA preparation, were the model itself, the secret recovery process, and then the secret verification. So all of these things are things that can be improved. So we can keep doing research to get better models, better optimizations. We keep working on that. Over time, we've now developed like 5 different cryptographic distinguishers that can recover more and more complicated types of secrets. That's improving the secret recovery part. And then finally, the secret verification, in fact, that's really the statistical part. So bringing more complicated or sophisticated statistics can also help to recover secrets better. The SALSA performance, the one thing I wanted to note is that We don't even need the models to be particularly good at predicting B as soon as they start to learn. So what you can see in this graph here is this is the loss dropping. As soon as it starts to drop, and this is the accuracy of predicting B, so even just 25% accuracy of predicting B, these dotted lines are when we start to recover the secrets. So you don't even need high accuracy models in order to be able to recover the secrets with our distinguishers. So I'm not going to go into how the distinguishers work. I'm happy to talk about that more at the reception if anyone wants to ask me. But all of the kind of limitations in our first SALSA paper, we've been able to remove in the subsequent SALSA papers. So bringing down the number of samples that we need to train on, improving the dimension. Increasing dimension is not hard for us. The machine learning models do not scale badly with dimension. So we can attack problems in dimension 1024, which is not typically something where you can run lattice reduction. The Hamming weights we're improving, continuing to increase the Hamming weight and the distribution of the secrets. So the kind of benchmarking results that we released in May, if you want to go to the website, even if you just Google LWE benchmarking, there's like a unique site you will find. So you'll find this URL. And what we did was what I said in the beginning, we released, the paper's already published, but we released the code, the models, and the data. So it should be all reproducible. Keep in mind, though, these are not deterministic. These are like randomized algorithms. So these are results that we've recovered over time. Unless you use the same seed, random seed that we use to train our models, you will get different models, you will get different results, but using our code, you should get ballpark the same results. So in the benchmarking paper published last month, we also compared it to all state-of-the-art methods for recovering secrets. And so what you can see kind of very briefly, I know there's a lot of numbers on this slide, but at the top row here, we have the unique shortest vector approach to recovering secrets. And these columns, this is for Kyber and this is for homomorphic encryption. And so you can see in these examples in Kyber and homomorphic encryption, general lattice reduction using USVP doesn't recover anything. It recovers no secrets despite having run these models for months and months and months. And then down here, you have a decision version, which is a meet in the middle. And this is a more lightweight approach that is well understood because it uses kind of exhaustive search, so it scales exponentially badly with the complexity of the secret. And so you can kind of see we've recorded like the complexity of the secret here in these numbers and then the amount of time used to train. So using the machine learning approach of SALSA from a year ago and what we call the cool and cool approach from a year ago, which is also a machine learning based approach, you can see that, for example, for the standardized homomorphic encryption parameters of dimension 1024, we can recover like binary secrets these are ternary secrets in roughly 35 hours, like with Hamming weight 8. The cool and cool approach can recover Hamming weight 12 in something like 21 hours, and meet in the middle can recover something like Hamming weight 9 in 65 hours. So these are just some of the work that we've done recently to try to make this approach more accessible to the community. As I said, people can take our models and our data and try to do improvements from the machine learning point of view. I'd like to point out that there's a lot of work to be done. This is just the beginning of using machine learning models in cryptography. And so I'll just kind of skip to my conclusion slide, which is that what I like to say, my conclusion from all of this is that we're now in an era of post-AI cryptography where we should be considering AI's ability to attack our underlying mathematical problems and underlying crypto systems, not just an era of post-quantum cryptography. So I like to give a shout out to all of my collaborators, which includes many different PhD students who have been interns and some of whom have gotten great jobs. So first author on the SALSA papers, Emily Wenger, who's an assistant professor at Duke University now. I'd also like to give out a shout out to some related work, which includes the work that Francois Charton has done in using AI to attack math problems such as learning linear algebra, the GCD problem, modular arithmetic, like I talked about. And for example, our Win6 project with my co-authors listed here, which was on learning modular multiplications, which was published last year. So of course, I would like to end with a picture of Win, so the Women in Numbers. This is actually the original wine, which happened at Lumini in 2013. I don't have pictures of all the other Win conferences, but I think I recognize some of you in the audience from this picture. So thank you so much for listening, and I'm sorry for going over time.